In this video, I'm going to give a high-level overview of Ethereum scaling, specifically the relationship the underlying node hardware has to scaling the layer 1 system, and why we can't simply increase the gas limit or make block times quicker to actually achieve real scaling. I'll briefly touch on some of the scaling solutions that are being worked on, but I'll go into more depth on these in a future video. And in fact, this video will be a part in a series on Ethereum scaling, in which I'll cover the broader Ethereum scaling roadmap, optimistic rollups, ZK rollups, optimism, Arbitrum, StarkX, StarkNet, and so on. Also, huge thank you to StarkWare for supporting this video series with a content creator grant. Very much appreciated. Thank you, thank you. And okay, so in order to understand Ethereum scaling, we should remember what Ethereum is and what it's trying to be in the first place. So Ethereum is a state machine, and state machines move from one state to another according to some rules. In the case of Ethereum, the state, the world state, is the set of all of the Ethereum accounts and their balances and nonces, as well as all of the contracts in the entire system. So all of the contract accounts, the code associated with them, and the storage that they have. So if you took a snapshot of the entire Ethereum system, all of this data at a given point in time, that would be the world state at that point in time. And the system, it moves from one world state to another as a result of transactions. Each transaction represents a usually very small change to the world state. And of course, the transactions are bundled up into blocks. So the world state changes in these steps every, say 13 seconds when a new block comes in. What I'm illustrating here in this diagram is just, we have this world state, call it world state sigma. And this world state is the result of applying all of the transactions in block sigma. So here in this diagram, I'm showing the world state and how one of the results of the block, or the only result in the case of this diagram, is that a new contract was created. It has some storage, right? There's two storage items here. It's got some contract code associated with it as well. And boom, that's it. A new block comes in, there's sigma plus 1. It has some changes in it. So we move from world state sigma to world state sigma plus 1. So here a new externally owned account, a regular Ethereum account, has been created. So you can see that here in pink. Whenever there's a change to the world state, because the Ethereum world state is organized in this Merkle-Patricia tree data structure, what happens is any change that happens in that tree structure, the data is stored down in the leaves of the tree, like the lowest level of the tree. And any changes that happen there, they trickle up to these intermediate nodes, and ultimately they trickle up all the way to the state root, like the very top root of the structure. So anytime there's any change made at all to the world state, it will result in a new root hash, a new fingerprint of the world state. Here we've created this account, results in a change to this parent intermediate node. And that ultimately will always change the root hash, the state root for the entire world state. And then again, here's another block. This is sigma plus 2. So here, this contract that we deployed up here has now had a change to its storage. So the contract storage here is shown as its own little tree. And it's a Merkle, I don't know if it's a Patricia tree. It's a Merkle tree for sure. So the change that has occurred here, we've added a data item. Before there were 2. Now there's 3 data items. That's altered the structure of that little tree. And that change has trickled up to the contract itself, where the storage root is stored. So because we've changed the storage, that changes the storage hash associated with that contract. And that trickles up to this intermediate parent node. And that trickles up to the root hash for the entire world state. So this is kind of the flow of how the world state changes. This is kind of the state machine way of viewing Ethereum. Here I've got a diagram kind of building off that idea. So the way Ethereum and most of these decentralized crypto systems work is you have many computers in a network, and they're all essentially performing the same tasks. So here, every machine is keeping track of the entire world state. As the new blocks come in, as new transactions happen, all of these computers are sort of moving in lockstep together, all computing the changes that are contained within those blocks. So they're all kind of naively replicating the work. They're all computing for themselves each transaction. Like if you do a Uniswap trade, the network has to calculate how that your trade is going to change the state of the Uniswap contract, or one of the Uniswap contracts, right? That pool is going to change. That has to be calculated, and the way this is done is that all of the nodes essentially do it themselves. They all do it independently. And you kind of need that for the decentralization and trustless aspect of these systems. So what I'm kind of showing here, just to explain the diagram a bit, because it's kind of cool. This is supposed to be the EVM, this little rectangular module up here that's connected to the world state, right? And this little EVM here, so we have a stack. The EVM is a stack machine. So it has this little stack for storing data. It has a addressable memory here. It has a program counter, a gas counter. We have a little ROM module here. So this is where the EVM would pull in the contract code associated with a contract, like this one here. And then there's a little section here for pulling in the storage associated with a contract and potentially mutating it, right? This is just a way to, visually represent the system. What I'm trying to show here again is that each node, each computer in this network is maintaining a complete copy of the world state, and it's running its own EVM. These nodes are connected, but they're really all doing this work, replicating it on their own, not trusting anybody to do the work and tell them the result, right? Okay, great. So we have this network of computers. They're all replicating this work. They're all keeping track of the world state. They run their own EVM, and they're all computing these changes and performing this world computer task, right? So how do we scale it? Because right now it's not very fast. Can't we just require that they do more work? Ethereum has this gas limit for each block. The gas limit is basically setting a limit on the amount of computational work that we can ask the network to do each block, right? So why don't we just turn that up? Or we could maybe just make the block times faster, right? So the block times, they have changed a bit over time. We can, there's nothing stopping us from decreasing the block time. There's nothing stopping us from increasing the gas limit either. It's been changed before. And this is the approach that some other networks have taken, actually, right? So Binance Smart Chain is a fork of Go Ethereum. It's basically an Ethereum fork, but with its own clean state. They basically did this. They have really fast block times, so they're like sub 1 second, and they increased the gas limit, to 78 million. Whereas in Ethereum, the gas limit is 30 million, but that's like the EIP 1559 burst limit. It targets 15 million. So on average, the blocks are going to do 15 million gas work of computational work per block. And Binance Smart Chain, BNB Smart Chain, they just tweaked a couple of these variables, and there you go. It's like 100x faster or whatever, 100x cheaper, assuming the same demand. So why don't we just do this? Could it be that simple? So this just increase the parameters approach to scaling is actually what Elon Musk suggested we do to scale Dogechain, right? Increase those parameters and then it wins hands down. The problem with this, of course, is as you increase those parameters, it becomes harder to run a full node, right? If you start increasing the gas limit really high and making block times really fast, you need a higher end machine to run a full node and to stay synced in the network. And that costs more money, so less people are going to do it. If you continue to push that, if you turn the gas limit up really high and the blocks are really fast, then you get into the situation where you kind of need to be in a data center to even stay synced with a network, or you need really good network conditions. And the best network conditions tend to be in the data centers. And data centers also have all the climate control and all of these redundancy and power and all of these things that you want if you're running like a $20,000 machine or whatever it is. As you start tweaking those parameters, you pretty quickly massively reduce the number of entities and people who are running those full nodes. And you really want regular users to be able to run a full node, which Vitalik explains here. The approach being taken with Ethereum has been to kind of target a $2,500 mid-range machine as, something that could run a full node. Because if you make it kind of a mid-range consumer accessible machine like that, then regular people can run them, and they will. That kind of sets the performance characteristics of your network in a sense. You need to choose what kind of level of hardware you're going to require to run a full node, and that will determine the performance characteristics of the network from there. And you don't want the machine to be running at 100% CPU. So really you need to choose what price level of machine do we want a full node to be able to run on. And then you need to make sure that, you're only using like 5 to 10% of the CPU and not a crazy amount of bandwidth and not a crazy amount of storage. So I've summarized that data here. We want, 5 to 10% of CPU to be used on block verification, 1 to 5 megabyte blocks every 12 seconds or so, and like half a terabyte of storage, right? And like I said, for Ethereum, it's like $2,500 machine. Bitcoin, I think, is like Raspberry Pi range. So say like 250. And yeah, if it's high cost, it's going to be high performance, but higher barrier to entry, fewer nodes, low cost, many nodes, right? So it's a trade-off. So again, the performance of your layer 1 is determined to a large degree by that target, that machine that you're targeting, whether it's $2,500 or $250 or like 50 grand, you can decide whatever you want, but you're trading off decentralization, you're trading off the number of nodes. And that level of performance, that price point that you choose is going to determine that layer 1 performance. And as the innovation continues in the hardware space and you can get more compute and storage for $2,500, then we can raise the gas limit and you get a little bit more performance over time, right? Because $2,500 in 10 years buys you a lot more compute than it does now. So for reference, I actually run an Ethereum node under my desk there, video footage below, and it runs perfectly fine. I spent about $1,500 Canadian on it, parts off Amazon. That's like $1,250 USD or something like that. And it has no problem staying synced with the network. It runs perfectly fine. You can see the stats here, 32 gigs of RAM, 12 cores. And here's the Go Ethereum dashboard. So you can see how much memory Geth is using, and it's staying synced to the chain head. This part's interesting. You can see the block processing time. So when a new block comes in, my node has to process it and, compute the state changes and all that. And the amount of time it takes to do that computation actually varies quite a bit. And this is interesting because, most of these blocks, they do vary thanks to EIP 1559, how much work there is in a block. But on average, they should average out to about 15 million gas, right? But the processing time does tend to vary quite a bit. And sometimes it'll spike up to like 1 second. Usually it's like 250 to 300 milliseconds, but you'll get these big spikes. And this is actually interesting because this is part of the function of gas pricing, right? Like, so the EVM has all these operations that it can do, and those operations are using my underlying computing hardware. They're taking up disk space, they're taking up storage space, they're taking up CPU time, etc. So part of what's trying to be done here with gas pricing, with pricing these little operations in terms of gas, units of gas, is to try and actually map the amount of computational work it takes to perform one of these little tasks to like the actual hardware cost that is being used when you perform it. Doing an add operation is pretty cheap because it's really fast for my CPU to perform a simple add of two 256-bit numbers, right? That's super easy for it to do. But if you want to store some data, right, like S-store here is 100 gas. So you're storing this data for a long time, maybe forever, right? So it costs more gas because it costs more underlying resources because it's using up my hard drive. You know, doing that little add operation just uses a bit of CPU time. Doing the S-store is using up storage on the entire network. So in pricing these EVM operations in these gas units, what the core developers are trying to do essentially, or one of the things they're trying to do, is have the load on the underlying node hardware to be somewhat even. You want to price these operations so that you don't have a block that comes in with, say, if one of these operations, like a hash, was really badly mispriced, like it was priced way too cheap, then you could have 15 million or 30 million gas worth of these operations in the worst case. And maybe it's actually taking my computer a long time to compute those hashes. So 30 million gas worth of them, maybe it takes me like 30 seconds to process that block. Now you get this kind of DDoS scenario where if this block comes in with perfectly legitimate transactions that just happen to be like a whole bunch of hash executions in some contract, that block comes in and suddenly, instead of 250 milliseconds to process a block for the average machine, it's taking like 10 seconds. And now all those nodes are like barely able to keep up with the network, right? So one of the goals here with this pricing is to tweak the pricing on all of these operations until you don't have any imbalance like that. Ideally, it would be really smooth where every block, no matter what kind of transactions are in it, takes close to the same amount of time to process, and ultimately is costing the underlying infrastructure, the underlying node hardware, a similar amount of real world cost. You don't want it to be this really lopsided situation. Okay, so we have the situation where we have this network of computers. They're all keeping track of the world state. They're each running an EVM. They're kind of naively replicating the computational work to process the transactions. And you kind of need the situation to be set up that way because then it's decentralized, right? And you want to scale that system, but you can't just increase gas limit and make blocks really fast, because then you make hardware really expensive to run and you rapidly centralize the node operation, and then you defeat the whole purpose of the system. So how do we scale these systems? Well, there's multiple approaches. I would say the first one I have here, side chains and multiple L1s, this is not really scaling. I would argue, like, having a side chain, you're having a separate system. You're having another system. You're not really scaling a world computer or a blockchain system by having side chains. You're just, because you can bridge from Ethereum to Polygon proof of stake, for example, but that's a completely separate system. It has its own security trade-offs and its own amount of total assets staked and centralization of the stakers and all these things, right? So it's a separate system. You're not really scaling your L1. There are, for Ethereum in the future, we may actually see state and execution sharding, where instead of having like one, single threaded world computer, so to speak, you have like a multi-threaded, like 64 threaded world computer. So you split up the state and the processing of the transactions into like 64 pieces. And there's ways to do that where you're not reducing the security of each shard to like 1/64th the security of the overall system. You can like shuffle the validators and do all this stuff, and in theory achieve pretty much the same security of the entire system, but also have like 64 threads in your CPU, so to speak. The trade-off here is that it's complex and it's like a big engineering feat to pull it off. So it's somewhere in the future and it may not even happen. And fortunately, we probably don't need it, because layer 2 is where all of the scaling is now happening. And layer 2 allows us to compress transaction activity, to compress this like world computer activity without trading off security. So that's the approach that's being taken now. So there's many layer 2 projects operational now that are doing this compression, right? Here's some of them here. I'll talk about them more in a future video. And here's my final illustration. So what I'm trying to illustrate here is we have the Ethereum L1 here. These are the underlying nodes, right? And they're creating this layer 1 platform here. This is like the Ethereum platform, right? Each of these little squares is meant to represent like a regular externally owned account, where these bigger ones are like a contract. So, you know, a contract is maybe using more of the state, the Ethereum state, and maybe it's also using more of the capacity, like per block or per day. So think of the size as corresponding to like the amount of state it's taking up and the amount of the network that it's using, right? So we have a couple side chains here, and these are completely separate networks, right? They have regular accounts and contracts as well. So these can be fully Turing complete and all of that. But they're not on Ethereum, right? They're separate systems, and they have a little bridge, so you can potentially like bridge assets over, but you're on your own platform. It's a totally different thing. Then I have these, I'll switch to a better illustration. So these systems here, like all of these ones are on a higher layer, right? They're on top of the layer 1. They're a layer 2. And what's happening here is like you have this small amount of capacity, right? Like this is a contract here. It's a relatively small amount of space in the state, and it's using a relatively small amount of the throughput of the system. But because of this compression that you're getting with L2, with things like ZK rollups and optimistic rollups, you have all of this extra, like a huge number of accounts, a huge amount of activity is compressed down into this tiny space, right? And that's what all of these systems are doing. And like with the layer 1, what I'm trying to show here is these little squares are like accounts and these bigger ones are contracts. So you can have this entire platform here, like this one's StarkNet, and you can have this entire Turing complete smart contract platform that's running on Ethereum essentially, and you're compressing all of that computation and storage and all this. And I'll explain how all this works, but you're compressing it down effectively into like a tiny little footprint. And the amount of compression you can do is actually insane. Like we can get massive scaling just by doing this L2 compression kind of thing. And we can have this whole ecosystem of all of these different L2s with all of these different properties, and they can all run with the security of the L1, which is like the holy grail of scaling, right? So you keep the L1 simple. It just executes the contracts associated with these layer 2 networks, and boom, you have scaling, which I will talk about in the next video. And finally, this is the approach that Ethereum is taking. It's going all in on layer 2. So that's how it's going to work. Okay. Thank you for watching. I will have more videos as soon as I can. Okay, I hope that wasn't too long. I'll have more videos soon. Thank you. Bye.